Hi, everyone. Thank you so much for attending today's webinar, Before It Becomes 3D HP, Validating and Ingesting Elevation Derived Hydrography at the USGS. My name is Emily. I'm the Chief Technology Officer at the National States Geographic Information Council, or NSGIC. If you're unfamiliar with NSGIC, we exist to advance effective national coordination of geospatial information by supporting state-level cooperation. We serve as a national forum for the development of capable and future-oriented geospatial leadership. If you'd like more information, please visit our website, www.nsgic.org. A couple quick housekeeping reminders. Everyone's been muted upon entrance, and there will hopefully be some time at the end for Q&A. So please hold your questions until the end of the presentation. And like I said earlier, yes, this will be recorded. And the recording will be made available to all registrants and also in the NSGIC knowledge base. So thank you so much for joining today. And I'm going to turn it over to the presenters.
Thank you, Emily. Hello, everyone. Thanks for attending our presentation today, Before It Becomes 3D HP, Validating and Ingesting Elevation Derived Hydrography at the USGS. My name is Lily Nicknami, and today I'm joined by John Tellini and Haley Thompson. We are all cartographers at the National Geospatial Technical Operations Center. Next slide, please. The National Geospatial Technical Operations Center, or NGTOC, provides leadership and technical expertise in the acquisition and management of trusted geospatial data, services, and topographic map products for the nation. One of the program missions is production of hydrography data, which we will be emphasizing today. Next slide, please. To start off, we'll touch on the differences between the hydrographic data used and produced by USGS. In the presentation today, we are covering specifically the production of 3D hydrography program data and the validation of elevation-derived hydrography data sets. Other hydrographic data sets provided by USGS include WBD, NHD plus HR, and NHD. For the rest of the presentation, we will refer to the data sets that we're emphasizing as 3D HP and EDH, respectively. Next slide, please. So this diagram displays how the USGS elevation and hydrography products work synergistically. Coarser resolution 3-depth products, specifically the 10-meter DEM, were used to inform the production of NHD plus high resolution, and finer resolution 3-depth products, specifically 5-meter for Alaska and 1-meter for CONUS, are used to inform the production of EDH and 3D HP. EDH represents the surface water interactions using points, lines, and polygons, and the EDH are primarily derived from 3-depth data sources and derivatives. Now, the goal of EDH is to acquire new standardized hydrography data for the nation that aligns vertically, horizontally, and temporally with 3-depth data. The EDH follows specifications and goes through rigorous validation before being accepted for production because EDH is the foundational data set that is used for producing 3D HP data. So 3D HP really marks a new era for surface water mapping. It's the first systematic remapping of the nation's hydrography since the original USGS 1 to 24K scale topographic mapping program was active. The intent of 3D HP is to improve the discovery and sharing of water-related data by providing users with a 3-dimensional hydrography network that's generated from and integrated with elevation data. 3D HP includes attributes, catchments, and flow network derivatives that increase the utility of the data for modeling and other analysis purposes. Now I'm going to pass it over to John, who will discuss the elevation-derived hydrography validation process.
Hello, everyone. As Lily stated, my name is John Tellini. I've been a cartographer with NGTOC for about 7 years now. I started with USGS on the 3-depth validation team. For the past couple of years, I've been working in the hydrography section as a product owner and workflow coordinator for EDH validation. I want to thank you all for giving me the chance to share some of the EDH data validation process with you today. So let's get started. At the base of the validation process, we have our data providers. The acquisition of EDH data comes from various data providers, including geospatial products and services contracts, or GPSC, or financial assistance contracts, which are both offered through the data collaboration announcement, and contributed data sets. From these different acquisition mechanisms, each data provider uses diverse processing methods to generate products for EDH. So it's important that each individual data set can pass our validation checks to make sure that the data are suitable for inclusion into 3D-HP. Since we receive data from different sources, it is important that we have a way to guide data providers to make consistent EDH data. And that's where our acquisition specifications come into play. They define conditions and parameters used when creating EDH datasets and help guide data providers to create consistent data structure for a national level dataset. As stated earlier, EDH is the backbone of 3D-HP, so it's very important that we evaluate it in a cohesive manner to make sure that these data can be transformed into our final product. Each of the specifications released with the same year correspond to a unique version of the EDH geodatabase schema, which serves as a template for our data providers to delineate EDH features. Each revision consists of updates and clarifications for representing data in the schemas. Our validation tools are capable of validating data in any of the EDH schemas. However, it is up to the data provider to make sure they follow specific schema versions in relation to their acquisition contracts or specific guidance from USGS. This graphic is a simplified version of the EDH validation workflow and consists of three phases. The first phase of this process is the data download. It consists of transferring data to an internal storage location from a repository hosted by the data provider. Steps that take place in this phase prepare the data for our staging and validation processes. Staging is the second phase of this process, and it consists of performing further documentation review as well as automated and manual checks on the data delivered. These checks are critical for the data to be able to be processed efficiently in our workflow. So we can think of these as checking the foundational structure of the data set in which the rest of the geometry and attribution of features is built from. Validation is the final stage of the cycle and will determine if the data will be passed to our production team for inclusion into the 3D-HP data model, or if we will be requiring corrections for the data provider before it can be used. This process constitutes a deep dive into feature-level geometry and attribution in relation to the elevation surface and specification requirements. The logic and functionality built into these processes is largely derived from data templates, our specifications, and guidance documents that inform data producers on how to derive features. Over the past few years, we've made a number of significant improvements to the overall EDH validation workflow. A few examples are the introduction of standardized processes for our data download and staging, comprehensive checks for the DIM and EDH spatial metadata requirements, the ability to assess updated EDH schema versions, and a standardized delivery structure, which we will cover on the next slide. So this is the data delivery structure we now require for EDH deliveries. This standardized structure, along with the data download workflow, alleviates any confusion around deliverable versioning and streamlines the data access for the staging and validation checks. Due to time constraints and the extensiveness of our validation process, we'll only have time to cover a limited number of deliverables here and the checks that are associated with them. First deliverable we will cover is going to be the source DIM used to derive the EDH features. We'll cover the EDH geodatabase, which contains all of the hydrographic features delivered by the contractor. The EDH spatial metadata deliverable. This includes working at boundaries as well as elevation source information. And finally, a review of the geomorphic indicator raster and how it is used. So the first deliverable, again, we will cover is the source DIM delivered by the data producer. These DIMs are comprised of 3-depth original product resolution data that are mosaiced together to create a continuous elevation surface to derive the EDH features from. Data producers are responsible for any geoid updates, reprojection, or raster mosaicing that takes place in the creation of these raster files, and explicit guidelines are outlined in the EDH acquisition specification for generation of these deliverables. It is good to note that the spatial reference information applied to the data is region-specific. For example, we use a horizontal EPSG code of 6350 for CONUS and 3338 for Alaska. And then a combination of automated and manual checks are done to ensure the quality of these deliverables. Some of the automated checks that take place for the DEM, most of these checks occur in our staging process. So it's important to catch any errors with these DEMs as soon as possible, as they serve for the base for creating the EDH data itself. Our tools have default parameters that can be applied to the assessment based on regions such as DEM resolution, projection information, etc. So walking through the list of checks, we have our spatial resolution, which assesses DEM pixel size. We have our origin and bounding coordinates check, which supports expected projection grid compliance, the linear units used by the projection, EPSG codes assigned for projected and vertical coordinate systems. We have valid minimum and maximum elevation values. This check mostly helps when no data values have been updated in the header information of the raster, but not in the raster elevation band itself. We have a check for the no data value specified in the header information as well. Check for any no data cells that exist within the specified boundary of the work unit, plus a 250 meter buffer. And the data coverage check ensures that we have DEM coverage for all of the delivered EDH features. The GT raster type geokey check finishes the assessment of the grid compliance, and it ensures that the pixel origins start in the upper left corner of the pixel. And then finally, we have the GeoTIFF key revision check, which increases the software compatibility of this data. The DEMs used in EDH are derived from two distinct elevation sources, one based on IFSAR-derived 5 meter grid resolution products for Alaska, and the other based on LiDAR-derived 1 meter grid resolution products for CONUS. The nature of the interpolated surface from the SAR imagery differs from surfaces interpolated from a LiDAR point cloud, and therefore the hydrographic data resulting from these sources is slightly different. So we used to have different teams handling these regions, but over the past years, the workflows between the IFSAR and LiDAR-derived data sets have been integrated. And while retaining some small differences in the context of error outputs due to those resolution differences, the tools and reporting mechanisms are now the same. So aligning the validation workflow allowed for anyone on the hydrography validation team to take on any of the incoming data sets and provide consistent reviews. This effort required creating new workflows, cross-training our staff, and newer updated tools capable of testing both IFSAR and LiDAR-derived data requirements. With the completion of this workflow alignment, our review times have been reduced by half. The next deliverable we will cover is the EDH geodatabase. There are 3 layers that exist in this deliverable: are polygons, lines, and points. Each feature class has a list of hydrographic feature codes that can be used with each geometry type. Also, a significant set of parameters used for the feature classes in the geodatabase are the coordinate resolution and tolerance, X, Y, and Z resolution of the feature vertices, which is the precision of the coordinate measurements, is set to 1/10 of a millimeter, while the X, Y, and Z tolerance, which is the minimum distance for coordinates to be considered coincident, is set to 1 millimeter. And the reason this is an important parameter to understand with this data set comes in when we create a network of features. For features that share coincident nodes to represent network connectivity, Vertices must be within a 3D distance of less than or equal to 1 millimeter. The checks performed on this deliverable during the staging process include our unique ID check, which ensures each feature delivered in the EDH geodatabase has a persistent identifier to use during the validation and production processes. This attribute is assessed to ensure no null, empty, or repeated values are present. The geodatabase schema checks compares the general structure of the delivered geodatabase to a template we provide for contractors to use. Again, this check ensures that there's a consistent standardized structure of the database being used when we're getting data from different sources. Our projection information check compares the spatial reference object of the delivered geodatabase to the schema template. Each detail of the projection information is expected to match, and this includes the spatial reference type, projection code, spatial reference domains, tolerance, and precision. The Z-enabled check confirms each delivered feature class is Z-enabled to accept the elevation values on the feature geometry. The geometry check uses a combination of open source and ArcPy-based geometry reviews to assess if the feature geometry is valid. This is done to help ensure geometry compatibility across the geoprocessing software spectrum. Also checks for multi-part and non-sample geometries of features. And finally, the coded value domain and subtypes check assesses additional required feature attribution for null values, gives feature counts by name, and assesses the domains and subtypes associated with each feature class, ensuring that they match the schema template. Outputs from these tools include a summarized text report, as you can see in the image here, alongside feature class outputs that contain the validation check attribution. All right, so now we'll get into the main validation checks that are performed on the EDH geodatabase. Again, with the limited time I have to go over the details, I will only be covering a few of these checks. So the first check up is our unintegrated vertices check. It is relevant to know that the linear features have a threshold in which the vertices are allowed to be below the elevation surface. And that depends on the remote sensing equipment used to create the elevation surface. For LiDAR-derived elevation surfaces, vertices can be sunken up to 1 meter below the surface and still not be called as an error. For IFSAR-derived elevation surfaces, vertices can be sunken up to 2 meters below the surface. The logic of this check works by creating a selection of line features based on a combination of attribution. These are then separated into two groups, lines that are allowed to have unintegrated vertices, which would be our breaching features such as culverts, terrain breaches, pipelines, underground conduits, and then lines that are not allowed to have unintegrated vertices. Each group is assessed for vertex Z values compared to the coincident DEM pixel value, and differences are reported in the output. Again, this tool returns statistics in a text report and then also generates feature class outputs delineating where issues are found. If any issues are found, they're then reviewed by the validation team and communicated to our data producers. Next check we will touch on is the network trace check. This builds a geometric network from the delivered EDH lines based on the three-dimensional coordinates of the start and end vertices of features. It generates network connectivity information for use by later tools and traces the network to provide a summary of connected network segments. Outputs that are generated by this tool include all the nodes in the geometric network generated from the lines, any network end nodes, which represent outflows to neighboring areas if located within a working boundary, or isolated networks if identified within the work unit boundary. Multi-part line features that represent every EDH line traceable from each network end, and any looping features found in the network trace, ensuring an acyclical representation of the network. In the example, we can see that the network end has been generated in an area where the start node of the downstream feature is not within the XYZ tolerance of the upstream end node. The last check we will review is the GMI capture conditions. We will go over an in-depth review of how the GMI raster is made later in the presentation. But for the purposes of explaining how this validation check works, we can summarize the GMI as a raster comprised from 4 different elevation derivatives that attempts to identify channels in the terrain. So this check assesses EDH line feature types that have requirements based on indication of channelization in the elevation surface. The way this check operates is by completing 2 assessments based on feature type. The first assessment, test A, checks features by length within GMI indicated channelization. And the second assessment, test B, checks the features by length outside of the GMI indicated channelization. The check outputs a texture report of results as well as features that do not meet specific testing criteria. The outputs are then assessed by the validation team and reported to our data producers. The next deliverable we're going to cover is our EDH spatial metadata deliverable. This is an important addition made to the EDH deliveries in recent years, as this geopackage contains 4 layers that assist in the validation of the EDH data. Those layers are the defined project area as seen here, or DPA, which represents the original contracted boundary of the EDH work unit. The final deliverable project area, or FDPA, which includes any adjustments to the contracted boundary to include any necessary network features. The elevation project polygons, which define elevation sources used for the production of the Mosaic DEM deliverable. And the DEM limitations layer. This identifies the areas of the elevation surface which are not suitable for deriving hydrography. In this graphic, we can see that the defined project area was expanded to include features across the international boundary to complete the hydrographic network. In these areas, 3-depth data is unavailable, and internationally harmonized NHD features will be used instead for the horizontal geometry and attribution of the features there. However, the FDPA is not just for use to expand into international areas. In the image on the left, we can see derived EDH features that are continuous and extend outside the border of the DPA in green. In the image on the right, we can see that the boundary of the DPA has been modified to include these features that would now be used as the FDPA pictured in pink. We do ask that when generating an FDPA that the 3DHP web feature service is used to exclude features that would be draining into neighboring watersheds. And this minimizes the number of inflow and outflow features that cross a boundary, just promoting the continuity of network features contained in our work units. All right, now we will go into the geomorphic indicator raster, or GMI. So again, put simply, it is a raster that attempts to identify channels in the terrain. The generation process uses a smooth DEM to generate derivative values from a variety of analytical techniques and then are combined into a final raster. The EDH acquisition specification provides parameters for all of the processes used in the GMI creation. The process is as follows. The input DEM is smoothed using feature preserved smoothing. The maximum allowable absolute elevation change parameter limits the replacement of a smooth DEM cell elevation value to within a half meter of the original DEM cell value. The smooth DEM is then used to generate the following derivatives in no particular order. A geomorphon's landform classification is performed. Geomorphons 9 and 10, the valleys and depressions, are used as indicators of channelization. Geomorphons 2, 3, and 5, the peak, ridge, and spur, are used in the final GMI raster to set the coincident cell values equal to 0. The black top hat transform outputs a raster using multiple closing windows. Values greater than the processing parameters listed for each window size are used to indicate channelization. And essentially, this performs an image analysis highlighting darker features in a grayscale image with different window sizes for assessment. Next, we have the multi-scale elevation percentile outputs. And this outputs a raster where the percentile values less than or equal to 10% are used to indicate channelization. This assesses pixels' relative vertical position in relation to other pixel values in the processing window. And then a magnitude raster is generated where the most extremes are farthest away from the 50% mark. Finally, we have the d-infinity flow accumulation output raster, where accumulation values over the specific thresholds here are used to indicate channelization. Once all of those derivatives are created, the binary outputs where these parameters are true are added together, and any cells where those geomorphons are equal to 2, 3, or 5, those are set to 0. So the result is that higher values in the GMI output represent areas more likely to be channelized because it's represented by multiple derivatives. So values represented in this raster, they range from 0 which equals no indication of channelization to 4, which is a very strong indication of channelization in the surface. The raster is then used to guide the integration of EDH features both horizontally and vertically with the elevation surface. To finish the data validation workflow, results are compiled into a validation report and communicated to internal staff and the data producer. If corrections are being requested to a standardized report, if corrections are being requested, a standardized report of any issues found with the accompanying geo package containing the delineation of features requiring corrections is communicated to the data provider, and a redelivery of the data is requested. If the data is being accepted by the EDH validation team and plans to be passed to the production team, a report is also generated communicating the passing validation conditions to both our data providers and the 3DHP production team. All right, with that, I will pass the presentation back to Lily to review the ingest process and convert the EDH data into 3DHP data. Thank you all.
Thank you, John. So many of you in the audience may have either been directly involved in or are familiar with the National Hydrography data set and have heard of 3DHP prior to this call. Today, Haley and I will walk you through the evolution of the data from NHD to 3DHP, discuss some of the phases of our ingest workflow, and touch on some challenges and lessons learned thus far. Next slide, please. So as the NHD sunsetted, the framework of the 3DHP data model was being built in tandem. A final snapshot of the NHD was loaded into the 3DHP data model to create the initial skeleton of the 3DHP. I will refer to this initial skeleton of the 3DHP as the source data in later slides, so just a note there. This load process involved crosswalking NHD features to their corresponding 3DHP feature types. Now, one of the overarching goals of 3DHP is data model simplification. So to achieve that, some of the NHD feature types were combined into one 3DHP feature type. Most of the NHD flow lines have a one-to-one relationship to their 3DHP counterpart, but some have a one-to-many. Next slide, please. As you can see, for points, lines, and polygons, there can be a one-to-one or a many-to-one relationship depending on the feature type. Next slide, please. So how do we take the initial 3D HP skeleton and create the elevation derived 3D HP product? As you can see in this diagram, there are quite a few steps required to turn EDH into 3D HP. The first step is that the EDH contract is awarded and data is delivered and inspected. Now that's what John just discussed in detail. If the data fails inspection, it does go through cycles of corrections with the data provider until the data meet our specifications. And if the data passes inspection, it's accepted and ready to begin the ingest process. If an EDH dataset is not already in EDH schema 1.4, it does get converted to schema 1.4 before it goes through our ETL or extract, transform, and load process. Now, this process converts the EDH data to the 3D HP schema. After we do our ETL process, we then conflate the main stem IDs and GNIS IDs from the 3D HP source data to the target data, which is our EDH data that's converted to the 3D HP schema. After the automated conflation process finishes, there are a series of manual error fixes that are completed to make sure that the main stem IDs and GNIS IDs are getting conflated to the correct features between the source and the target data. Now, this part of the ingest workflow, the manual review, is the most time consuming, depending on the complexity of the new hydrography and the size of the work unit that we're processing. After our manual error fixes are done and we clear out all of our error tables, we move on to generating new main stems to any new tributary or feature that got edited during that manual editing process that needs a new main stem ID assigned. After we generate all of our new main stems, we create our flow network derivatives and our catchments. Final data preparation is the last step that's run before we do our manual verification of our tables and attribution before passing our data onto our data management team to load the data. Our data management team runs a process to replace the new data in the enterprise database, and then they create an extract, which is passed to our delivery team to publish the data to the 3D HP all service, which is how it gets to the public. Next slide, please. There are 17 phases that are executed to transform the EDH data into 3D HP. The screenshot that you're seeing is of our tools that we use to run this workflow. We like to group our phases into data prep, conflation, catchments, and final data prep and review in our workflow. Now, currently our tools are standalone Python scripts that are executed in ArcGIS Pro, but eventually they will be integrated into a user interface to streamline the tool execution process. Next slide, please. So the data preparation phase of our workflow is comprised of 4 phases. Those include post-validation data prep, which is currently done outside of the tool. That's the part of the process where we convert an EDH data set that's not in schema 1.4 to 1.4. ETL, hydrolocations and external updates, and vector setup. So as I mentioned previously, ETL translates that EDH data to the 3D HP schema, and it also loads the data into a geodatabase that will be used for ingest processing later on in the workflow. Hydrolocations and external updates places our initial hydrolocations on the network and assigns the hydrolocation feature types based on a series of business rules that we have integrated into the tools. This phase also updates the flow network table to account for any external connections between processing areas that we have. And our vector setup sets the backup working in production directories in our workspace. So it really does workspace prep, and then it also filters any features that participate in catchments for catchment generation later on in the workflow. Next slide, please. So EDH lines map to 3D HP lines in various ways. As you can see on the diagram, some features have one-to-one relationships and some have one-to-many, depending on their elevation classification or E-class attribution. So based on the E-class, the 3D HP feature type, mapping may change. Everything that you're seeing on the left, so the mapping between the EDH lines and the 3D HP lines, have a one-to-one conversion. But if we take a look to the right, we have different conversions based on E-class. So for example, some canal ditch EDH features are 3D HP canals, while other canal ditch EDH features will become hydro-enforced connectors. And again, that's based on the F code E-class combination. So a canal ditch line with an E-class of 0, which means it's not used to create elevation derivatives, will map over to a hydro unenforced connector in 3D HP, whereas a canal ditch line with the E class of 2, which means it's a linear feature that follows the elevation surface, will map to a canal in 3D HP. Next slide, please. Here are the additional schema changes for polygons and points, and as you can see, the polygon and point conversions are a one-to-one relationship. Next slide, please. So after the data goes through our ETL process, our hydrolocations are generated, and hydrolocations are points along the network that signify important locations such as confluences, termini, headwater, and other types. Currently, our hydrolocation feature types are generated based on those business rules. So we have a pretty extensive set of business rules that determines where on the network a specific hydrolocation feature type can be placed. And right now we have 11 hydrolocation feature types, but we may add more in the future as the 3D HP data model develops. Next slide, please. I do want to note that some of the hydrolocation feature types are brought in from NHD, namely those are the reach code start, reach code end, and then we do have some springs and sinks that were ported over from NHD as well. Sinks are unique as in that they may be collected as part of the EDH delivery as well. Next slide, please. So now let's take a look at an example of how a hydrolocation business rule is applied and translated in the 3D HP data. So for headwater hydrolocations, one of our business rules is that a headwater hydrolocation must not begin at a drainage way and instead must be placed on the downstream channelized feature that's not a drainage way or elevation breaching connector. The reason why we do that is because drainage ways are, I don't want to say artificial representations, but they're not representing direct evidence of channelization. So instead we place the headwater hydrolocation on the next downstream channelized feature, which if you take a look at the top right portion of this graphic where we have the highlighted drainage way in cyan, the blue point that's directly downstream on the headwaters of the river feature is where the headwater hydrolocation point is placed in this case. If you take a look to the northwest of the graphic, there's a river that goes all the way upstream to a headwater hydrolocation point. And in that case, the headwater hydrolocation is placed at the true headwaters of the river. Next slide, please. After the data preparation phases have been completed, we move on to our conflation. Now, conflation in our context is the process of transferring main stem IDs and GNIS IDs from the source data, so that source 3D HP, to the target data, which is the EDH phase 3D HP. Conflation consists of 6 phases for us. The first phase performs the initial spatial buffering and matching of our main stem and GNIS IDs from the source to the target features. Now, for those of you who may not be familiar, main stem IDs are a cross dataset identifier for all flow lines that represent the headwater to outlet path of a river. And GNIS IDs are permanent unique numbers assigned by the Geographic Names Information System, or GNIS, to a geographic feature name for the sole purpose of uniquely identifying that name. In the next part of our conflation process, we generate temporary flow network derivatives to further assist in finding candidate matches for the remaining unassigned main stems. Now, essentially what this process is doing is it's taking our temporary flow network derivatives and it's extending a main stem ID assignment all the way up to the headwaters as much as possible. And this is helpful for us because it reduces the amount of errors that we have to manually review at the end of our conflation tool sequence. Our polygon conflation transfers GNIS IDs from the source to target polygons. And after our conflation process is run, we get a series of error tables that are generated that we need to manually review and edit to ensure data integrity before we generate our new main stems. As I mentioned previously, this part of our workflow on the ingest team is the most iterative and the most time consuming to review any misassignments in main stem IDs and GNIS IDs. After we clean out all of our errors, we do generate new main stems. So any feature that has an unassigned main stem, this could be due to the retirement of original main stem due to a drastic change in the geometry between the source and the target features, or just simply the presence of a new feature in the target data that didn't exist in the source. We see that quite a bit because of the new density of the hydrography that we're seeing. And so any of those features that need a new main stem get a unique main stem assigned to them. And then finally, we generate our main stem log table. Our main stem log table stores important information about main stems within our processing area, and it crosswalks any main stems that were retired to their new main stem ID. So it's just a tabular tracking mechanism for us for our main stems. Next slide, please. So some of the biggest challenges that we've encountered in conflation thus far are dealing with discrepancies in spatial representation. Now, the NHG and EDH are really vastly different in many areas, both in delineation and in density. And this makes the conflation of the GNIS IDs and main stem IDs particularly complicated in areas of complex hydrography, such as braided channels and karst areas, are two of the main examples that we've seen so far. And in those areas specifically, our manual QC takes more time. As with any automated process, there are limitations. And while our conflation methodology is robust and we've gone through many iterations of improving our code and our processes, it's not perfect. And sometimes the process will misassign IDs that require manual editing. So to address some of the challenges that we faced last fiscal year, we have modified our conflation methodology to reduce the amount of main stem and GNIS ID conflation errors. Specifically, we're reducing the amount of false positives that we're getting in our error queues to save us time in our manual error review. And we've also developed internal processes to expedite error review in ArcGIS Pro using a series of queries and other tracking mechanisms to speed up the process as much as possible. And in many cases, we also collaborate with other SMEs to make sure that we represent the extent of a main stem or a GNIS ID correctly. Conflation can be somewhat subjective, and oftentimes we have to make our best judgment call. Next slide, please. Some of the most common scenarios that we see during conflation are the addition of new channel lines, removal of old channel lines, and length differences between the source and the target data, which is primarily what you're seeing in this graphic here. The red features that you're seeing on the graphic are the old data, and the blue is the new elevation derived hydrography data. And you can see particularly in this graphic along the extent of the main stem that there's pretty good match. But in the tributaries, we have quite a bit of length differences in the addition of new channel lines, new tributaries that did not exist in the old data. During our conflation error review, we examined various error classifications for both main stem IDs and GNIS IDs. And these include gaps, which are gaps in the GNIS ID or main stem ID. Gaps can be caused because either it's a true gap in the network due to the presence of a sink or an invalid gap in the ID because of our buffering process misassigning an ID to an incorrect part of the network because of the proximity of the buffers. We also see branches. When we see a branch in an ID, it's commonly due to a target feature getting assigned the main stem or GNIS ID of the main stem because of its proximity to the feature that it actually should have been assigned to. We see mismatches, which are errors that are flagged when the source and target flow line have a length difference of over 2 kilometers. So very likely, I don't have the exact error types displayed on this graphic, but very likely where I put length differences on the graphic is an error that would have been flagged as a mismatch because of the length difference between the source and the target data. As you can see, the old data extends much further up into the headwaters, and the elevation derived data is telling us that actually the headwaters of this flow line starts further downstream. We also see missed error type, and these are main stem IDs or GNIS IDs that get missed or are not assigned to a feature in the target data. Now, these are often valid errors and are due to the fact that the feature no longer exists in the target data, or the spatial representation of the target feature is really just too different from the source, so that main stem ID or GNIS ID got missed. Next slide, please. Karst areas really have presented a unique challenge for us so far because the presence of sinks often create gaps in main stem IDs and GNIS IDs. There are two types of main stem IDs that we deal with during conflation. Those are our community reference main stems and USGS main stems. We try to preserve our community reference main stems as much as possible because of their historical precedent, and USGS main stems are generated in-house. We try to preserve those as much as possible, but we do prioritize those community reference main stems when we're doing our review. In this specific example, we had a sink cause a gap in the reference main stem, The sink point is highlighted for you in cyan, and it caused a gap in the new network, where in the old network there was actually connectivity in that reference main stem. So in this case, we had to get additional SMEs who had more knowledge about karst areas and have some internal discussions about how we wanted to preserve the extent of that reference main stem ID. And then also we had a GNIS ID in play in this instance as well. So we're definitely encountering some complexity as we process these work units. Next slide, please. I will say that our biggest challenge by far is conflating these IDs in braided channels. So as you can see, the source data that's in red, target data in blue are extremely different in this braid plane. Now, there are many features in the source that no longer exist in the target, and parts of the braid plane are actually getting collected and represented differently as far as being represented as one-dimensional or two-dimensional features. And because of our buffering process, how we assign our main stem IDs and GNIS IDs, complex braid planes like this are very, very challenging for us, and they require the most manual review. Now I'm going to pass it over to Haley to talk about the catchment generation phase of the process.
All right, thank you, Lily. So for the remainder of the presentation today, I'm going to touch on some of our derived products that we produce for 3DHP. So after completion, we hit the next block of tools, which is dedicated to the catchment workflow. For those that aren't aware, catchments are essentially a polygon feature class that encompass the area around each flowline feature from which that feature would receive water from the landscape. So we've touched on vector setup already, but I do want to reiterate that vector setup is the first main tool we run as part of the catchment process and is used to prep the vector components of 3DHP for use in catchments. So just again, to reiterate, this step creates a backup of the geodatabase within the working folder. So we mainly do this to help stop corruption of geodatabases by not editing our final database directly. It also predetermines which features in the flowline, hydrolocation, and water body feature classes will be used for catchments and also for hydroconditioning. We also get an extract of surrounding 3DHP data at this step. So that we do this because it helps us better enforce the boundaries of catchments, especially at the inlets and outlets of our processing areas. Once vectors have been processed, we then switch to raster prep, which begins in this hydroconditioning step. So in this step, we use all of the necessary raster functions to derive where the water will flow to on the map. We do this by burning features into the raster and then creating a series of derived products like flow accumulation and flow direction. I'll also go a little bit more into hydroconditioning in a few slides. So the last two primary catchment steps are catchment setup and catchment processing. This is where the catchment polygons are initially formed, first at an initial 1-to-1 catchment to feature ratio, and then aggregated into their final form in the last step. So lastly, we do have some validation that we do for catchments. And this does things like check proper attribution, as well as look for any anomalies within the data. So as I mentioned, the vector setup tool will predetermine which features will be used for catchments and for hydroconditioning. For each attribute, we have a value of 1, and that means the feature will be used in catchments or hydroconditioning. A 0 value means we did not use those features. This is not exclusionary. A feature can be used in catchments, but not hydroconditioning, and vice versa. And so I've listed the list of reasons why we would exclude features from either attribute if they meet one or more of the conditions listed. And just as an example, I will go through the flowline feature class. So for hydroconditioning, we have less rules. We filter out using attributes coming from EDH, and that is E class and F class. So anything with an E class of 0, meaning it does not participate in creating elevation derivatives, we would exclude, and F class of 2, which are features captured outside of EDH specs. For catchment processing, the features that actually get catchments, we're a little more strict. So we do things like filter out features that would be smaller than the diagonal of a cell. We don't actually expect to see this. This is just kind of a validation on our end. Again, those E class and F class values are filtered out, same as hydroconditioning. We also filter out drainage ways. Those do not participate in catchments, and anything that is upstream of a hydrolocation point, a headwater hydrolocation point. We also do not allow elevation breaching connectors that are attached to drainage ways. One hydrolocation feature that we do use in catchments will be sinks. So anything that is not a sink will be filtered out. Sinks, whether they are on or off the network, do participate in catchments. Just want to note that as well. So hydroconditioning is one of our most processing heavy steps that we use as a part of calculating 3D HP. First, within the tool, we've set up our standardized parameters that will be used throughout the hydroconditioning portion of the process. So this includes flow accumulation, which is a threshold we use to identify stream networks, our minimum burn depth for sinks, and burn depth for participating flow lines. And both of the latter are in meters. We do have a difference in burn depth for CONUS and Alaska. This is due to our resolutions in the DIMS that we use. So our initial step in hydroconditioning is to copy and prepare the hydrologic features. This is where we pull in the flow lines that we determined are going to participate, as well as any surrounding data from other work units that we would like to use in processing. We flatten water bodies, which flattens the cells underneath lakes to a minimum elevation that exists within the lake polygon. Densifying unenforced connector features with a density factor of 0.5, as I mentioned above. This converts lines to a raster product and burns the streams into the DEM. Next, we will identify both sinks and terminus hydrolocations and converting those into a raster product that will be used for masking. Next, we condition the DEM by combining stream rasters created earlier by burning the streams into the DEM using the Z values on streams are available on those flow line features. This is also where the burn depth parameters applied to the stream pass. We also apply the stream mask at this step. During the computation of elevation derivatives, we will fill sinks, compute that flow direction raster, compute the flow accumulation raster, and convert any significant sinks or sinks that are deeper than that minimum depth parameter above to polygons. Finally, we use the delineate watersheds tool within Pro using a seed raster of the flow lines and sinks, as well as the flow direction raster. So once again, this is our last step, the final raster product that we get from running the hydroconditioning part of the process. And it looks like this kaleidoscope of catchments. At this stage, it is still a raster. We will convert it to polygons in the next state, or the next part of the tools. And just as a reminder too, I did want to show these rasters, but we do have flow accumulation and flow direction. We currently are not distributing these rasters, but again, I wanted to highlight them here as well. So I'm going to look at things in a little bit of a different way. So what does this look like at a smaller scale, and how do we use the vector flow network to build the catchment product? So let's start by looking at this network here. So this might surprise a lot of you, but I will note that this network is very simple compared to the one that we actually work with in 3D-HP, but I think it will serve as a good example. Also, as we discussed before, not all flow lines will get catchments, but in this example, I am going to allow all of them to participate. So all of those individual colors are individual flow lines, and the gray dots are our hydro locations. So after hydroconditioning and catchment setup steps are ran, we get something like this. So as a reminder, the catchment setup step turns the catchment raster product that we created in hydroconditioning into our initial vector polygons. So these are our initial one-to-one catchments, meaning that at this stage, every sink and participating flow line has an individual catchment assigned to it. This is going to be our most similar representation to what we had in NHG plus HR. However, there are still some key differences. So one of the key differences that we now include in 3D-HP are headwater catchments. So headwater catchments, again, are new in 3D-HP and are intended to capture the areas above headwater points, and in general are used to capture the greater area of flow into the start of a network. Just for reference, I've symbolized each of these catchments individually, but the outlines are symbolized by the difference between headwater catchment and flow line derived. The green are our new headwater catchments. the green outlined ones, and the blue are our flow line derived catchments. So lastly, in catchment processing, we aggregate catchments based on the network. So this is now shown by the black outline. But backing up a step, to aggregate catchments together, similar to how we use a temporary attribute for catchment processing and hydro conditioning, we have another temporary attribute we just call catchment group or catch group, which is seen in the image above those numbers. This applies a unique value to groups of flow lines along sections of the network where we want catchments to aggregate into a single polygon. Where these aggregations occur is where our hydrolocations are placed at confluences and divergences along the network, and those are heavily used in this part of the process. So in general, we consider these areas of uninterrupted flow, and we aggregate those into a single catchment. And so as you can see, several aggregations have taken place. While every catchment, with the exception of headwater catchments, gets that catch group attribute, that doesn't mean that every single catchment is an aggregated polygon. And I've pointed out the aggregated ones with those red arrows there. So as I mentioned, we will see that catchments will go from hydrolocation to hydrolocation, confluence to confluence. But what other types of situations would essentially stop that area of uninterrupted flow and stop catchment aggregation? One of these things might be sink. So in this example, I'm going to add a sink feature, and I'm going to reaggregate. So this is what we would have in our final product. So with the introduction of a sink into the network, this is no longer considered an area of continuous flow, and we update our catchments accordingly. Other things, other than, as I mentioned, confluences, divergences, etc., that would stop aggregation are water body outlets and inlets. So while we do currently have to use temporary water body inlets, those are not part of our hydrolocation feature class at this point. We will be adding them in a future update of 3DHP, but we do use temporary ones to create catchments now. So the final product would be something like this kaleidoscope of catchments. So I also want to point out one of the new things in 3DHP is the main stem. As Lily mentioned, we do conflate those onto our flowline feature class, but they also get applied to our catchments. So any catchment that you can select using a main stem of the flow line should also be selected by that exact same attribute, tying those together. So after catchments are created, we move into our last block of tools. This tool section will finalize the attributes in the tables and the feature classes. Specifically, these steps will address the main stems, including adding logic for main stems into the flow network table and transferring main stems onto the catchments, but also hydrolocation and water body feature classes. This step will also address our flow network derivative calculations and any additional attribution and validation checks that are needed at the end of the process. It will also create an AOI, an area of interest polygon, that is used to update the data in the service with the 3DHP data that we have ingested throughout this toolbox. So within the flow network table of the final product, some of the new attributes we have are up main and down main. These attributes indicate within the flow table at each record whether or not the main stem identifier has continued to the next flow line. So I'm going to walk us through a quick example just to kind of show how this works. So I'm also specifically going to use the down main attribute for this example. So I'm going to give each of these a unique identifier. I'm just going to use 1, 2, and 3. So let's say that the main stem in this particular part of the network at this junction flows from 1 to 2. In this case, the record from the flow table for 1 to 2 would be true, indicating there's a continuation of the main stem from the upstream feature to the downstream feature. However, there's another record in the flow table from 1 to 3, and the down main record for that would be false, indicating that the main stem does not continue downstream. So also done in the tools, as I mentioned, is the application of the main stem to all features along the network. So as seen in this example, hopefully the video is playing for you guys. Main stems are particularly useful after the step because it links all features interacting along that section of flow to the same main stem value. So you could select all of those with that same main stem. It's playing again, 1 second. Okay, so now I'm also going to briefly touch on the flow network derivatives, which is another add-on that we offer in 3D-HP. So flow network derivatives are a set of 16 network attributes, which will be populated in their own table within the 3D-HP geodatabase, but they will be connected directly to the flow line and catchment feature classes through ID 3D-HPs. For those of you that are familiar with NHG plus HR, the logic behind how these are calculated will be largely similar, but not necessarily identical to the VAAs or the value-added attributes that we had in NHG plus HR. This is simply just because we have different attribution and feature classes available, so we had to update the logic of each to match our current schema. As these attributes are derived from the network, the calculation of these attributes often need to be ran in a specific order, as they will use previous flow network derivative attributes to build upon their respective logic. So this is because many of them, again, use the flow network derivative attributes as parameters in their population. So for example, I'm gonna use level path ID. As we mentioned before, level path ID is an identifier that is used to link together paths of the network as it moves downstream. It is generally 1-to-1 with our main stem attribute, so it's indicating a main path. It's a good attribute for that. So to calculate this, we have two attributes here, start flag and terminal flag, that kick things off, indicating headwaters and terminus points along the network respectively. From that, we get arbolate sum as inputs. Arbolate sum, again, is the summary of all flow lines upstream at any point on the network. That is an input into hydrosequence, which is is applied to each individual flow line in like a sequencing order, indicating that the lower you are in hydrosequence, the farther down you are on the network towards the outlet. And lastly, all of these attributes contribute finally to level path ID's population. So this is our table in our 3D-HP product. This is all the attributes that we offer. It's important to note, once again, we have two attributes here, ID 3D-HP and catchment ID 3D-HP, that will link these flow network derivatives to both the flow line that they participate on, as well as if there is a corresponding catchment to that flow line, it is linked here as well. So let's revisit level path ID just for a second. So as I mentioned, this attribute is useful in identifying the main path throughout the network. So in this example, I have used level path ID of the highlighted flow lines to select what I know as the main path through the network due to the outlet. That's the, and also using this attribute, I'm going to link a few other attributes to gain some useful information. So using the level path ID of the outlet feature, as we saw in the previous slide, I'm going to select all features with the corresponding and the matching terminal path attribute. So terminal path indicates the most downstream feature on the network. So everything that flows to a network end will have the same terminal path ID. Again, I'm going to bring up arbolate sum just as to show you here. So add the outlet of the network for this level path ID. We also are able to look at the arbolate sum attribute. So this indicates the total length of flow line for all of those selected flow lines upstream. However, this is not only at the end of a network that you could use this information. You can select any flow line along this network and know the arbolate sum of that feature. So in the final moments of creating 3D-HP, we copy the data back into the production folder that we established at the beginning of the process. We then review data outputs before the data is sent for load in the enterprise database. We do use an erase replace process that updates the completed NHD to 3D-HP and replaces it with the new EDH source 3DHP product. The finalized data is then used to update the national map service endpoints, and it becomes available for use. So I've linked here some helpful information. So you have the National Map Delivery website, which we can send the link out for as well. I see that it's just the name, and the USGS 3DHP page, which will tell you a lot of additional information about 3DHP and the program that we work on here. All right, we have reached the end. So I'm sure if there are any questions, we can now take them.
So I'm seeing a few questions in chat. I think a few of them have been addressed. So thank you, Steve and Lily, for taking care of some of those in the chat. But the first question I see is, will these tools be available to the public in the future? And if this is your question, feel free to come up and clarify.
So the question is asking if we will be able to provide the toolbox that we're using to ingest data. That's not currently the plan. No.
Question mark. Oh, yeah. How much time do you typically spend on mainstem ID compilation for each delivery, and at which points in the process does manual review occur? And if this was kind of addressed during the presentation, feel free to say that.
Yeah, so it kind of depends on the size and the complexity of the work unit. So say, for example, we have a smaller work unit that's less complex. Maybe we have a higher match between the source and the target data because the grade plane is not very complicated, or it's a headwater unit. I would estimate that at about a week. And then it can be 2 weeks and beyond if we have a larger, more complex unit. And just keep in mind, we sometimes will have failures in our software, or we have a karst area that we need to bring in SMEs on before we make any final decisions. So all of that can weigh into the time that it takes to wrap up the conflation before we can move on to the next phase of the workflow, which is then assigning those new main stems before we pass the data off to Haley. So I would say anywhere between a week to, I think the longest we've seen is about a month, but that was for an extremely complicated data set. So, we don't know moving forward, that could change depending on the complexity that we're seeing this next fiscal year. But also we are making a lot of improvements to our conflation process and to our internal workflows. So it's variable. Sorry, I don't have a specific answer for that.
Yeah, no worries. Thank you. Yeah. And my apologies if I'm asking questions out of the chat that have already been addressed. It's hard to keep track of. Let's see. Is there a minimum size of the catchments that will be delineated?
No, we do not have a size requirement necessarily for catchments. We do review any that we have a tool, an automated check that points out if things are small, like really small, and we will review them for accuracy at that point. But we do not have a size limitation on catchments.
Okay, just a quick follow-up on that. The reason I ask is because some data providers are offering buy-ups such as catchment delineation. And I'm wondering if that's money well spent, if you guys are going to essentially be doing a very similar thing.
So do you want to... Thanks, Milana. I was just coming off mute for that. Steve, I think that's sort of up to you to weigh, but I will emphasize that there will be catchments in 3DHP generated during the ingest process as described here. And if catchments are produced by a contractor or vendor, they almost certainly will not match the catchments that are produced through 3DHP. So I think it's a good question. You'll have to answer it for yourself, knowing that there will be catchments coming to you.
Okay, that's very good to know. Thanks, Sue.
You bet, Steve.
Thank you. I also see a question here. Flow accumulation thresholds were shown a couple of times. Could you speak to whether / how these thresholds are determined for different areas?
That is a great question. I am having trouble recalling off the top of my head. If you wouldn't mind shooting me an email about that, I will definitely get you an answer. I'm Haley Thompson, by the way. My email is linked on this slide. So feel free to take that down.
Sounds good. Will there be an API to access the data?
Steve, I don't know if you or Sue want to take that one, but you might be able to speak to it better than we can.
Lily, Steve had to hop off for another meeting he's presenting today. I don't have the answer to that, so we might have to defer to Steve. I don't know that an API is in the plans right now, but don't take that for gospel until we ask Steve for the definitive answer.
All right, sounds good. And I think finally getting down to the end of the questions in the chat. Is there a plan to update all 3DHP to the newly launched NAPGD 2022 spatial reference system?
This is Lily. I don't know off the top of my head. We'll probably have to follow up with internal SMEs and then get back to you all. So I'll provide my email in the chat, and whoever asked that, I'll follow up with you.
Yeah, that's good. And last question I see here is Hawaii processed same as CONUS's, which is LiDAR and 1 meter resolution?
I can take that one. Hawaii would be processed in different horizontal spatial reference and vertical, I believe, from CONUS. There are, believe, different datums that would be used for both of those. And we haven't processed any of the data for Hawaii yet, but I could let you know what the plan is as far as serving out those regions if through email, if that would work.
And John, I'll just hop in and note that baseline 3DEP for Hawaii is LiDAR. So the baseline for processing 3DHP in Hawaii would also be LiDAR and 1 meter resolution. I'll also note that most of you know, but some folks may not know, that the data acquisition regime for 3DHP is different from NHD. So it's a partnership program similar to 3DEP. So Hawaii isn't necessarily in plans until we have partnerships in Hawaii, at least at this moment. But when we get there, it will definitely be LiDAR and 1 meter resolution.
Thank you. And one more question came in here, which was, how does 3DHP handle change? Either change in dynamic stream channels, like the braided river example, or change in base data access, improve DEMs, for example?
Emma, I think that's a programmatic discussion. Right now we're focused on sort of the baseline mapping of 3DHP, but knowing that, of course, hydrography does change. So we need to work through what that looks like. But if there's a particular area of change that we've already mapped, and a partner has need and we have new 3DEP data for it, we would work through how to do a partnership to get the information updated. There may be a potential for some sort of a DEM limitation, but I don't know that. We haven't worked through what that would look like, so we'd have to work through that. Hopefully that answers your question.
Thank you. Yeah, and if that was your question, please feel free to come off mute to clarify. Okay, I see. Yeah, thank you in the chat. Awesome. Oh, sorry, I hope you can't hear my cat yelling in the background. Cool. Are there any other questions? And feel free to use the raise hand function. There are. Okay, well, I guess seeing no more questions, thank you so much again for the presentation.